Hello? Can everybody hear me up there? Can you guys hear me? Okay. So we're taking attendance again today, so please sign the attendance sheet as it passes you. If it already passed you, then when the sheets get up to the top, pass them all the way back to the front to make sure we get people who came in a little late. So today I want to talk about Alan Turing and the halting problem. We're going to prove that the halting problem is undecidable. We're going to show you that there's something that you can specify precisely and completely and mathematically succinctly even, but it cannot be solved using any algorithm. And that's one of his many contributions. So Alan Turing was a mathematician, logician, basically is a founder of computer science and many other fields, including artificial intelligence and cryptography. And he invented the first computation model. Before Alan Turing came around, we thought we knew what it means to compute. You know, people have been adding numbers together since pre-Roman times, but nobody really nailed down a definition of what it means to compute. And he's the first person to do that. He defined what it means to have an algorithm. And there were plenty of algorithms before him. We just didn't define them formally. We didn't think it was worthwhile doing, and we were very wrong about that, as he showed us. So he invented a so-called Turing machine, the very basic model of computation involving basically changes of states and a transition function and read-write tape. And that's really all it is, but it can do everything that we can think of that's doable, actually. So we'll talk more about that. He defined the notion of computable numbers and proved the undecidability of the halting problem, which we will do today. It's an amazing proof. He originated the notion of hypercomputation and oracles and devised the Turing test that tests whether something behaves intelligently. And that was the foundation of all of AI. This was late 40s, early 50s that he did this. And all of AI is based on his work and kept building on it. So he was his artificial intelligence pioneer. So he also invented neural networks upon which machine learning is built. And machine learning is now the basis of doing a lot of different things in industry and in everyday life. Self-driving cars have it in it. Your iPhones, your smartphones have machine learning algorithms in it. Amazon, Netflix, they use machine learning to do recommendation systems to figure out your preferences and show you ads. Google uses it. Basically, every company in the world now uses machine learning and neural networks. Well, he invented those too. And of course, he built one of the earliest computers in the late 40s. And as a sideline, he helped the Allies win World War II against the Nazis. That was just a hobby of his. And he defeated the Enigma machine, the German cipher. And of course, the Turing Award is named after him as well. So he gets a lot of credit for doing a great many things. And it's hard to overstate the importance of his work and his impact on our species. So here's Bletchley Park, where him and his colleagues broke the Enigma code back in World War II times, early to mid-40s. There's the machine he actually constructed to help facilitate the breaking of the code. It mechanically went through a bunch of permutations much more quickly than humans could by hand. And without this machine that he built, it wouldn't have been possible. So it literally helped save millions of lives and shortened the end of World War II. So many books and movies have been written and produced about his work. And most recently, The Imitation Game with Benedict Cumberbatch playing Alan Turing. For extra credit, you can watch it. I know many of you have watched it. How many have seen this movie, by the way? Okay, good. Well, just write a few paragraphs about what you learned there and how it relates to the course and what you thought was interesting, cool, exciting, and you get credit for that. I wish my professors would give me extra credit for watching movies when I was a student, but I wasn't so lucky. So, of course, we didn't have Netflix back then either, so, or Amazon streaming for that matter. So again, Alan Turing made a tremendous impact in a number of ways. Here's a program written by his own hand for the machine that he actually invented. So that's his debugging and programming right here by his own hand. And this will probably fetch a pretty penny on eBay, this document. And again, here are so many books about the impact of his work. It's pretty well known. Here's a few more books about his contributions, his breaking of the Enigma code, his founding of AI, his invention of the notion of modern computation. So he appears on stamps, and sometimes refers to not the ghost in the machine, but the ghost in every machine. Your iPhone is based directly on his work. So is every computer that we use today. There he is running around Princeton back in the 30s. He was actually a runner as well. And how did we thank him for all these contributions? Well, we killed him off for being gay. Back in the early 50s, it was illegal to be gay in Britain. But luckily, and kind of ironically, the British government finally apologized for killing him off for being gay. Basically, he was driven to suicide, as you see in the movie. The apology came in 2009, which was more than half a century later. That wasn't as late as another famous apology where the church apologized to Galileo 350 years later. Bottom line is apology, late is better than no apology, but sooner is better, as I always say. There's entire conferences to this day based on his work and paying homage to his work, investigating the implications of his work. It's still ongoing. So in the book, the stuff that we're about to talk about comes from pages 173 to 179, the halting problem and the undecidability of the halting problem. And you should please read about it in the book, as you should follow the book all along, not just watch the lectures, but it's important to read the book. You get a different perspective, different explanation. Sometimes the book gives you more details that we don't have enough time to talk about in class. So how many are looking at the book, reading the book, referring to the book? Only a third of you? Oh, okay, I want this number to be higher next time I ask you in a week. It should really be all of you. In fact, some of the problems on the homeworks come directly from the book. So I'm not sure how you're not looking at the book if you're working on the homework, right? So that's kind of an interesting riddle. Okay, so he showed that the number of algorithms, the set of algorithms, is a countable set. It could be put into one-to-one correspondence with the integers. And that's not to be taken for granted because some sets are not countable. We've already seen that the real numbers cannot be put into one-to-one correspondence with the integers based on diagonalization, right? But in terms of algorithms, you can sort the algorithms by size, and within size by lexicographic order, and then number them 1, 2, 3, 4, 5. So the smallest algorithm you can think of is just an empty program that does nothing, right? That's the shortest C program that's syntactically correct. You have to have an open brace and a closed brace, and the word main has to be there. So this algorithm doesn't do very much. It just begins and ends right away. But still, it's the shortest C program. So if you're sorting the programs in C, you can sort them by size. And here's a slightly larger program right here. All a program is a string, right? It's a string between quotes, denoting all the lines in the program. And carriage returns are also characters, so they're part of that string. So every computer program, every algorithm is just a string. And here we're sorting the strings by string length, by size. So there's a slightly larger program, and all of Unix operating system is a very large program, millions of lines of code. And somewhere down the line, you'd have Windows Vista or Windows 10 or Linux or whatever the latest operating system. That's an even larger program. The point is this list will have all possible programs in the universe, not just programs that have been written yet, but programs that will not be written for years or decades or centuries, and ones that may never be written because they're so large and complicated we will not think of them. But this list of possible programs has all the programs that an alien race have written too, in whatever their programming language is and however they choose to denote program lines and codes. So it's a canonical order. It's a list of all possible programs, and we now number them 1, 2, 3, 4. So this program will be number 1. This program is longer, so it'll be maybe number 9,300 something. It's just arbitrary numbers. But all the numbers are here, and all the programs are there. That shows you that the set of programs is countable. How many get this? Okay, good. So the longer programs might have very large numbers associated with them, but that's okay. And here's some super AI program that hasn't been invented yet for 1,000 years. That's okay. It's still on that list. It's on that list right now. We just haven't discovered it yet. Okay, so that's similar to the dovetailing argument of matching integers to rational numbers. We already seen this a couple of lectures ago, and that's based on the work of Jorg Cantor. So there he is smirking. So the set of functions, on the other hand, is not countable. Yes? What about? It's like for some length, you have a bunch of programs written at that one length. Oh, yes. So he's asking, what if several programs have the same length? And that can certainly be possible. In fact, an exponential number of programs could all have length 150, right? What do you do then? Interesting question. Well, how do you sort them on this list? Wait, but they're different programs. They may do the same thing, but syntactically they're different, and they should appear on this list even if they're have the same function. As long as they look different, they should both. Yes, so sort them within size by lexicographic dictionary order. So we all know what dictionary order is. A comes before B, B comes before C, and you can sort the special characters also in dictionary order. Numbers can come before characters, and special characters like exclamation mark and equal sign it can come, let's say, after the letters. Whatever the order is, like Unicode or ASCII character order, that's how you sort things within the same size. So that's not a big issue. But it's a good point that you need to nail that down and explain how that's sorted, right? So you can number them properly. Okay, so we're about to prove that the number of functions is not countable. This will imply that there are more functions than algorithms, even in theory. And therefore, some functions cannot be computed using an algorithm. That's an amazing revelation. It didn't occur to us as a species for thousands of years until Turing showed that that's true. It's an amazing result, actually. We thought that every function that you can carefully define and unambiguously state and mathematically, specifically and unambiguously define must be computable using some algorithm or another. The answer is no, it can't, not necessarily. Okay, and we're about to prove this. So why are there more functions than algorithms? Well, so we're going to focus only on Boolean functions. We'll show that there's more Boolean functions than integers, and therefore more Boolean functions than pieces of code, than algorithms, and therefore some functions cannot be computed using an algorithm. How do we show that, even for the Boolean functions? Why are we harping on Boolean functions here? Because you can show this result even for Boolean functions. Functions that take in zeros and ones as input and produce a single bit as output. That's a Boolean function. It works only on truth values, not on any other numbers or objects. Right? So the number of actual functions of other types is even larger than Boolean functions, right? Cosine and sine and tangent and square root and exponentiation function. These are not Boolean functions, and there's even more of those. So we'll show this result even more strongly just for Boolean functions. That it's uncountable. There are more functions that are Boolean than there are algorithms. Okay? So Boolean function has a structure that it takes in some number and it produces a 0 or a 1 as output because it's Boolean, right? So why are there more functions than integers? Well, assume towards contradiction that you had some table that lists all the possible Boolean functions in the universe. Every one that exists is in this table. So for example, the always no function, the false function, whatever you give it, it says false, is right on this first row, right? That's f of 1. So f of 1 of 1 is 0, f of 1 of 2 is 0, f of 1 of 3 is 0. It's always 0, so that's that function there. The function that's always true is on the second line, for example. This is an arbitrary listing, one row per function, but each row is infinite, and there's an infinite number of rows. And each row uniquely determines a particular Boolean function that takes you from a natural number to a truth value, 0, 1. So for example, this function here is true only on the evens, and it's false on the odd inputs. So this function is the parity function. It tells you whether a number is even or odd, true or false, whether it's even or odd. This one here, it's true on 2, it's true on 4, it's true on 8, it's zeros everywhere else. It looks like it's identifying powers of 2. How many see that? Okay, pretty straightforward. This function here, it's true on 2, it's true on 3, it's true on 5, it's true on 7, but not on 8 and 9. So what would you guess this function determines for you? Primality of its input. And on and on and on. So this is an arbitrary listing of functions. I don't care how this table was constructed. It could be constructed by you or by some omniscient deity that somehow divined the right table that includes every function in the universe that can possibly exist. Okay, so I'm not making any assumptions about what this table looks like exactly, except that it exists and it's just full of values, and between all the rows, they cover all the functions that can possibly be. Okay? Here's what we're going to do next, and this is quite a trick. We're going to go down the diagonal of this table and negate it. So we've already done this for the reals in diagonals. This is diagonalization coming up, just like we did before. We're going to negate the diagonal, so if it's a 0, we'll make it a 1. If it's a 1, we'll make it a 0, and so on. And once we do that, we have the negation of the diagonal, And down here, we're constructing a brand new function that has these truth values for these inputs, 1, 2, 3, 4, and so on. But this function here in red is different than any function that's a row of this table already. Why? Because it differs from each row by at least one digit, and perhaps by even more digits than that. And if it's two functions are different on at least one input, they're not the same function anymore. How many understand that, believe that? Okay. So here we are constructing in red a function that's not in this table, no matter how this table was constructed. Even using omniscience and omnipotence, this table is flawed. It's missing some values, like the one in red here that we constructed. Very powerful argument. This is diagonalization. So we're proving that we're not millionaires, right? Proving that you're a millionaire is easy, show me the money. Proving that you're not a millionaire, that's hard. You can't not show the money and say, I'm therefore not a millionaire. That's not a proof, because you may have assets elsewhere, and who knows? You may have a lot of Bitcoin. Don't buy Bitcoin, by the way. It's a scam. This function here is not in the table. And if it's not in the table is flawed, and so no table can be constructed that lists all the possible Boolean functions, which means they're not countable. There are more functions than there are integers. End of story. That's the proof. And this works for any table whatsoever. And that's one of the contributions of Cantor, and Turing built this argument on top of the diagonalization argument that Cantors give to us. Any questions about this? Yeah.
If we considered only finite inputs, would the set of functions be countable?
No, because, well, first of all, these inputs are all finite.
No, I mean a finite number of
inputs. Oh, finite number of inputs? Yes. So if the domain was finite and the function could only operate on, say, 4 things, and that's it, yeah, there's only so many Boolean functions on a few things. And that will be pretty quickly exhausted, and you'll be good. There'll be a finite number, in fact, not just a countable number. But most domains are not finite. Like the integers are not finite, the natural numbers are not finite, the rationals are not finite, the complex numbers, the reals, none of those are finite. Those are the interesting kind of sets. You don't want a function that operates on just a couple of things and nothing else, right? That's not, I mean, you could, but it's not that interesting as much as the other functions are interesting, right? I mean, if the cosine function can only take 3 values and that's it, and it was undefined everywhere else, it would still be a function, just not that useful of a function. That's all we're saying. Okay, so that's a non-existence proof. Those are hard to come by, because this is true that you cannot enumerate the functions no matter who's doing the enumeration. No matter how omniscient and omnipotent they will still fail. And that's not saying something derogatory about omniscient and omnipotent beings. It's just like saying, you know, such a being cannot find an integer between a quarter and a third. You know, it's not a fault of this being. It's just ain't there to be found and displayed and given to anybody else, right? So that's what we're saying here. Okay, so another interesting observation here that this is also a pseudo-proof, or really a proof also, slightly modified, that there are more real numbers than integers also. Why? Because you can put a decimal point right there, and that will be a real number between 0 and 1 displayed in binary. How many get that? Okay, so this shows that you cannot display all the real numbers in a table where the rows are countable, because there will be a real number here that's not in the table, and therefore there are more reals between 0 and 1 than there are integers all over the place. Okay, so so you might think, well, why can't you take this function here that's not in a table, put it first, move everybody 1 down like this infinite hotel business that we showed a couple of weeks ago, and now this function in red is in the table, and the table is now fixed. Why can't you do that? Because you can hit it again with the same diagonalization argument for the new table with this extra number in the first place, and now you'll have yet another number. So a table like that is really fatally flawed. It's beyond repair. Okay? Any thoughts or comments on this? This is pretty fundamental. So we just proved that there are more functions than there are natural numbers or integers. And there's an infinity of both. But the infinity of functions is bigger in this very specific, strong mathematical sense. And one of the implications of this coming up is that there are more functions than algorithms, because the number of algorithms is already countable. We saw that on a previous slide. You can number them, but you cannot number the functions. So this shows you their functions are uncomputable. There's no way to compute them now or ever, by us or by anybody else in the universe. as long as they're using algorithms. If they use something else to compute, I don't know, like magic, all bets are off. But this also says that magic cannot be implemented algorithmically. That's what this says also. So magic is not algorithmic. I'm not sure if Harry Potter fans would be happy to hear that or not, but that's the consequences of this logic, right? Okay, so the set of algorithms is countable. We've already seen that, and we show that by dovetailing. There you can count them by displaying algorithms as, say, codes. And which language do you use here for the code? Well, any language you want. We use C, but you can use C++ or Java or Python or any language you'd like. Or not even a programming language. You can use English if you want to describe an algorithm. Plenty of algorithms can be described and have been described in English for millennia, and nobody actually wrote code for them, and that's okay. But we also showed that the number of functions is not countable, right? And we do that using diagonalization. So the last two slides are summarized here. The proof for the first was dovetailing. The proof for the second was diagonalization. And this is true about the Boolean functions, not just any function. So imagine how big the true set of functions are, including functions on reals and functions on complexes and functions on matrices and on vectors and other things. That's even worse. It's even bigger. So this means there are more functions than algorithms, which means some functions are not computable by any algorithm whatsoever. This is not to say we haven't thought about the algorithm, or the algorithm is too big and too complicated for us to write down, or maybe in 1,000 years we'll finally invent it if we devote enough human centuries of effort to that task. No, that's not saying that. It's saying that such an algorithm does not exist for anybody to find ever, no matter what the effort is. And that's a very strong negative statement that we're making. It's very broad and encompassing, and it applies everywhere in the universe, not just here on this planet. So I want you to understand how audacious, how bold this statement is, this theorem. Right? It's an incredible negative result. Very disappointing to a lot of mathematicians around the time of Turing in the 1930s that didn't think that this could possibly be true. In fact, nobody even questioned whether it could be the case that for some problems that are very well defined, very precise, you cannot compute them using any algorithm whatsoever. In fact, they assumed the contrary. David Hilbert assumed that when he asked for an algorithm to determine whether any Diophantine equation has roots. He didn't say, give me an algorithm if one exists. He said, give me an algorithm, assuming that one must exist. They didn't question the existence of algorithms for certain problems up until Turing's time. By they, I mean the entire human race, and all of its mathematicians included, and scientists. Question?
So, by definition, algorithms have to be of finite length, and functions can operate on any number, like any number up to infinity, right?
Yeah, so algorithms must have a finite length, and they're basically represented as a string. That's not saying anything too onerous. That includes English description, codes, hieroglyphs, even a video with hand waving. That's an algorithm if you explain what you're doing. And take this whole video, all the bits of all the frames of the video, string it end to end. That's one big string. How many see that a movie or a video is one big string? Good. So it's not a big jump in abstraction to say that. So an algorithm could be a lot of different things, but there's a finite number of them because an algorithm has to have an end in terms of its description. Right? If you don't finish describing that algorithm, whether it's a piece of code or a video or English description, you haven't described it yet. So in order to finish describing it, it must have an end to the description, which means it's a finite length description, which means you can enumerate it like this, and we're good to go. Now, functions are just operations on some domain that give you some elements of a range, like the squaring function, quadratic function. So f of x is equal to x squared. So f of 3 is 9, and f of 5 is 25. And f is ready to operate on any number that you give it. If you say f of a Google, it's not going to say, oops, it's too large for me, I'm sorry, I can't do that. F will not say that to you. It will say, it's a Google squared. It's 10 to the 200. So f can operate on anything that you give it, assuming it's part of the domain. Now, if something is not in the domain, f will choke. So if I say f of my right shoe, the squaring function will not know how to square my right shoe. And then it'll be okay for it to choke and do nothing or be undefined on my right shoe. But my right shoe is not in the domain of the integers on which it's defined, so it's okay. Yeah.
This might be a dumb question, but
So when I say function, I mean a mathematical function, not a function that's kind of a code function. A code function is just another piece of code. When we say functions in code, like when you call a function inside a piece of code, yeah, you can think about it as an implementation of some mathematical function, but you can think about it as just another algorithm. And by the way, when you call functions in code, you can always unroll all the calls, take all the codes that you call, instead of calling those functions, take that code of that function and put it right there instead of the call, and now you don't have any more calls. You can always do that if you'd like. You can even do that with recursion if you're careful enough and use a stack to keep track of the recursion. So functions in code are not the same kind of beasts as functions in general. Those are more general than code functions. That's a good question. Yeah, question?
Do you have an example of a function that is not able to be computable?
That's not computable? Yeah, the halting problem, the halting function. The function of whether a piece of code halts or doesn't halt on a given input, that's undecidable, that's not computable, there's no algorithm. And we're about to prove that, actually. In a couple of slides, we will prove it. It's an amazing proof, actually. Yeah.
So by this definition, does an algorithm itself have to terminate? Like, does it have to terminate to be valid?
So an algorithm doesn't necessarily have to terminate, right? So if I say, here's an algorithm to print out all the prime numbers, it doesn't have to terminate because there's infinity of primes, and to print them all out one at a time and print only primes and not composites, not only it doesn't have to terminate, it better not terminate. It should not terminate, otherwise it's incorrect. And now an operating system is an algorithm. How many get that? An operating system is one big giant algorithm. Really? Only 5 people agree with that? Let me repeat. Think about it. An operating system for your PC, your laptop, your tablet, your iPhone in your pocket is one giant algorithm of 100 million lines of code. Oh, good. So you had me worried there for a second. Okay. So we're good on that. Now, an algorithm for an operating system, this algorithm doesn't need to terminate. In fact, if an algorithm for an operating system terminates, what is that called? It's called a crash. It should not terminate, right? So for an operating system to operate correctly as an algorithm, it better not terminate. So termination is not necessarily good, and non-termination is not necessarily bad. It's whatever the algorithm is intended to do. Okay. So I just give you some examples to illustrate that fact. Question?
Yeah, this is kind of off topic, but how many attendance sheets are going around and how many do we have to sign?
So you have to sign it only once, but one went for for each section of the course, each section of this room. So one went with the left side, one went with the right side. So if you have 2 of them, you just have to sign it once. Where's the other attendance sheet, by the way? Okay, good. So one is going in each section. If you haven't signed the attendance sheet, make sure you sign it. So when it gets to the end, pass it back to the beginning. And that's my algorithm to you for attendance, okay? It's an example of an algorithm that better terminate because I need the sheets back at the end of the talk, yeah. If it's full, well, you tell me, what's an algorithm to handle that case when the attendance sheet is full? Don't crash. What do you propose? Add another sheet to it, thank you. Simple, see, you guys are good. All right, what else? Okay, so there are more functions than algorithms, and in fact, there are more Boolean functions than algorithms. It's even worse than that. And in fact, not only some Boolean functions are not computable, there's no algorithms for them, but most of them are not computable. How many see why most of them are not? There's an uncountable number of functions and only a countable number of algorithms. And uncountable is so much larger than countable, even though they're both infinite. It's like the infinity of the reals versus the infinity of the natural numbers. They're both infinite, but there are much more reals than natural numbers. They're not even close. One is not the same as the other. So not only some Boolean functions are not computable, most of them are not computable. It's really pessimistic. This was really bad news for science and math in the 1930s when Turing came up with this insight. It's amazing we can actually add 2 numbers together, right? Given that most functions are not computable. Right? It's amazing that you can multiply things and do it, actually, because most things are not doable using algorithms. So in some sense, the things that we can do are very rare compared to the things we can't do algorithmically. Okay? That's just mind-boggling, right? In a minute, we'll see the proof for the halting problem being undecidable. Yeah.
Would it follow that an uncountably infinite number of Boolean functions are and would be not computable as well?
Yeah, an uncountable number of Boolean functions will be uncomputable. That's what this is saying, right? Uncountable. So uncountable being most compared to countable, right? So functions are a mathematical mapping from a domain to a range. An algorithm is a string. It's a piece of code. So he's asking whether a function is the same as an algorithm. So now I want to split that hair by saying they're not the same simply because there are different types, right? So it's like saying, you know, a zebra is not a mineral. What if you have a big mineral rock that is in the shape of a zebra? Would even stripes on it, some sort of a crystalline stripes on this zebra-shaped piece of mineral? Will it be a zebra then? No, it still won't be a zebra. Why? Because they have different types. One is an animal, one is a mineral. No matter what else is true, things of different types cannot be equal to each other. Now, that's not to say you can have a rock that looks a lot like a zebra, like a big statue carved by Rodin that has all the anatomically correct features of a zebra, but it's still not a zebra. It's still a rock or a mineral. So same thing for algorithms and functions. So they're not the same simply because they're different types. A function is a mapping, mathematical mapping from a domain to a range. An algorithm is a string representing a piece of code or a set of instructions or a recipe for cooking. That's also an algorithm. Take 2 eggs and a cup of flour and mix it. That's an algorithm. Every recipe in your kitchen is an algorithm. And so is every explanation, right, for anything is an algorithm too. But one is a string and the other one is a mapping from a domain to a range. So they're not quite the same. Now, having said that, a piece of code can implement a mathematical function. So you can have a piece of code that implements addition, multiplication, squaring, square roots, cosine, sine, and much more complicated things than that. But technically, they're not the same type of object. Yeah.
How do you distinguish between a guy with a pencil solving functions by hand and an algorithm? Because, I mean, you say that an algorithm is a string, but ultimately so is a function written on paper. It's a string of characters written on paper. Is that not an algorithm? Is that somehow different when some guy with a pencil goes and solves it?
Well, so the guy is not the algorithm, and the scribblings on the page are not the algorithm. They're little smidges of carbon, on a sheet of paper made of essentially wood pulp, right? So again, I'm being very pedantic about semantics here. So one can implement another, but they're not the same thing, right? So, but the guy with a piece of paper and a pencil is actually computing some function for some instance and is trying to figure out what the mapping to the range is for that instance and come up with the answer. And so he's implementing or computing that function for that specific instance of input. That's what the guy is doing. But he's following an algorithm that's in his head, or the algorithm could be written down as well, or it could be implemented in code and could be executing the code by hand, or it could be running it on his computer, on his laptop, and it's doing the work for him. So all these are modes of computation. Yeah.
But then does that not mean that either the guy would have to be unable to solve some functions by those corollaries, or he's not actually running an algorithm, he's doing something else?
So it depends what problem he's working on a piece of paper. If he's doing simple addition, yeah, addition is computable. Addition is not one of those functions. Or determining whether a number is prime. It's a Boolean function, prime or not prime, right? So Boolean primality detection function is one of these functions, but it's not one of those uncomputable functions. It's just one of the Boolean functions. That one happens to be computable. So I'm not saying no Boolean functions are computable, right? The AND of two things is computable. The OR, the XOR, they're all computable functions. Addition, multiplication, you can test for primality. You can even have machine learning algorithm that determines, does face recognition. In fact, your iPhone X does face recognition. It's a Boolean function saying, is it your face or not? It's a Boolean function. It's computable. It's implemented in silicon in that little box that's your iPhone X. So whatever it is doing, if he's doing it and he's succeeding in doing it, it can't be uncomputable. Otherwise, he will fail in doing it. If one of the problems that he's trying to solve is the halting problem, which we're about to show is unsolvable, he can't be doing that. And if he is still doing that, he's not using algorithms. He's using either magic or potions or clairvoyance or some other non-algorithmic method. So we're not saying it's impossible under every possible scenario, including Harry Potter scenario, where people wave a magic wand and stuff happens and nobody explains how. In fact, they can't. But that's okay. It's still entertaining. It makes a good movie. But as far as algorithms, it might very well be an impossible task. So I hope that helped shed light on your question and not confuse you even more, which I'm not sure what's the case at this point. Is that helpful? Or?
So basically
Yeah.
what you're saying is there's no distinction between the implementations of, how you run an algorithm, whether it's a computer or a guy with a pencil or whatever. These are, I guess.
Yes. Now you get.
It's not computable, it's also unsolvable.
Yes, that's exactly what I'm saying. It's not that the computer can't do this. A guy can't do this. A supercomputer can't do this. A cloud computer the size of the Earth can't do this. And an alien computer can't do it either across the galaxy, even though we have no idea how and what and what is this thing that we're talking about halfway across the galaxy, as long as it's doing things algorithmically, one step at a time in a stepwise fashion, they can't be doing it either. It's impossible for them too. In fact, it's impossible for a deity. And by deity, I mean something omniscient and omnipotent that can do absolutely anything that's doable. And by the way, there's limits even to what deities can achieve, right? A deity cannot find an integer between a quarter and a third, because it ain't there. It's not a matter of omniscience. It ain't there to be found. So it's not saying something, derogatory about your favorite omniscient, omnipotent, entity, but it's just a fact. There is no integer there between a quarter and a third, so nobody can display it to us because it ain't there. And we know that for sure. So an alien being race cannot do that either. And a guy with a pencil and paper cannot do that either. So coming up with an algorithm for the halting problem cannot be done to anybody. But, but you alluded to a very important point. Computation is a very general process. It's not restricted to iPhones or tablets or PCs or abacus or supercomputer or computing with your fingers on your hands. It's all of those and a lot more. Right? The whole universe is one big computer. It's an analog computer, and it runs on quantum mechanics, as far as we know right now. Right? So the universe is one big computing that's computing right now as we speak. In fact, we are all subroutines in this big computation that's going on. How many can see that abstraction? Okay. So it's a very interesting computation going on right here in this universe in which we inhabit. So that's how general computation is. It's all of reality as well. Right? Okay, anything else for now? All right. So most Boolean functions are not computable. We just saw that. But that doesn't tell us any specific function is not computable. We're about to show a specific one and prove it that it's not computable. And it'll be the halting problem. So the halting problem is a very simple problem. I give you a piece of code, right? And for that piece of code, I ask you the question, does it halt on this piece of input that I also give you? So I give you a program P and an input I, and both of these are strings. So a program P, like for prime numbers or an operating system or some other piece of code. P is a string, is a piece of code, is a program. I is an input, it's a data file. Now it happens to be that the data file can also be another piece of code. Right? A piece of code is also an input to some other code, right? Give me an example of a piece of code that takes another piece of code as input and does something interesting with it. Not a hard question. Compiler. That's what a compiler does every day you execute. It's a program that takes another program as input. It's perfectly fine to do that. Okay, so if you have a program and an input, both of which are strings, and I ask you the question, if you ran that program on that input, will that program halt or not halt? Which one will it do? Turns out that's undecidable. There's no algorithm in the universe to compute that. We're about to prove that. Now, that's a very simple question, and it's completely well defined. Whether a program halts or doesn't halt is not a deep, mysterious question. The answer is either yes or no. One of those two. It's not some third choice. It's the law of the extruded middle. There's only two options. A piece of code either halts or it doesn't halt. It can't do both, and it can't do neither. How many get that? It's a binary situation here. So it's a Boolean function. What's a Boolean function? That piece of code that supposedly tells you whether a program and an input as a pair halt or doesn't halt. The answer is very clear. So it's completely well specified, it's completely unambiguous, yet it's undecidable, it's uncomputable, there's no algorithm to determine that, as we're about to show. Right? So we could formally define h, this halting function, as a Boolean function from naturals cross naturals to 0, 1. Why naturals cross naturals? Because the program and the input can both be represented as integers themselves, as natural numbers themselves. How many could see that? Why? By this canonical ordering that we described earlier. Right? Every string can be represented as an integer. If nothing else, take that string, break it into the bits, and take those bits and interpret it as a number in base 2, and that's your integer representation of that string. That's one way to do it. There's lots of other ways to do it. Okay? So it's a function on two variables. It's a two-variable function, p and I, and the answer is either 0 or 1. It's 1 if the program p halts on the input I when you interpret p as an input and p as a program and I as an input. Otherwise, it's 0. If the program p on I does not halt, the answer is 0. If it crashes, I guess that's a halt. Right? If it runs forever, it doesn't halt. Right? So how many understand the definition of h? You just define a Boolean function on 2 inputs and 1 output. The output is either a 0 or 1. So it's a very straightforward, well-defined, crisp Boolean function. Okay? So you could also represent those 2 inputs as a single input if you'd like. If you say, well, okay, that's a function of 2 input. What if it was a function of 1 input? Must it be decidable? The answer is, of course, no still, because you could represent 2 inputs, p and I, as a single input, 2 to the p, 3 to the I. And if I give you a number of the form 2 to the 3p to the I, you can immediately tell me what p and I is. How many believe that? How would you do that? Why is that true? Why can you uniquely determine p and I if I give you a single integer of the form 2 to the p, 3 to the I?
Because you know how many, every number can be broken up into its prime factors, and 2 and 3 are both prime
Yeah,
factors.
unique factorization into primes. How many get that? So you can make p and I together into a single number and then feed that to the new h. And now h, first thing it does is disambiguates p and I from the single value 2 to the 3, 2 to the p, 3 to the I, and then works with p and I as the other h did before. So it's not a matter here of two input arguments or 1 input argument that's the crux of the matter. It's not. You can have it either way. Just as an aside. And by the way, the fact that you can factor every integer into unique primes, into primes in a unique way, what is that called? That theorem, it's a theorem. It has a name. It's such an important theorem, it has a special name. Anybody happen to know its name? It's called the fundamental theorem of arithmetic. Very good. The force is strong in you. It's good. Yeah, you heard about that. There's also a fundamental theorem of algebra. What is that? Every field has this fundamental theorem associated with it. What's the fundamental theorem of algebra? Take a wild guess. Yeah, every polynomial has a bunch of roots, as many as its degree, basically. I mean, if you have to go to complex numbers, so be it. What's the fundamental theorem of calculus? I'll let you ponder this one. Okay, so the halting problem is not computable. So that means we cannot detect infinite loops. Infinite loops are not just hard to detect, they're impossible to detect. They're basically asking the halting problem. How many had infinite loops in your code, ran into infinite loops, were you debugging, had infinite loops as an error mode? Yeah, most of you, of course. It's easy for it to happen. Now you know why it's so hard to predict and detect infinite loops. It's not just hard. In general, it's impossible. Now, in specific cases, it may be easy. Right? So if I give you this piece of code here, that's a complete program. How many say this program halts? How many say it runs forever? Yeah, of course it halts. It doesn't do much. It just assigns a variable, and that's it. That's a sad little program that doesn't do much, but the point is it halts. And it's easy to see that it halts. It's not mysterious, right? So the halting problem being undecidable, uncomputable, doesn't mean that you can never tell if it halts or doesn't halt. It means, in general, there's no single algorithm that correctly determines all cases. That's what it means. So this program here, another complete program, while true, begin, end. How many say this halts? How many say it runs forever? Good, it runs forever. It's an infinite loop that doesn't do anything other than continues to run forever, conditionless, right? So that really runs forever, and you can tell, and it's obvious. again, so this is another instance of the halting problem. But what if I give you a much more longer, complicated piece of code like Microsoft Vista operating system or Microsoft Windows 10 or Linux, whatever your favorite operating system is these days, and I ask you, does this run forever? That's equivalent to saying, does your operating system ever crash? And some of you are chuckling because, as you know, operating systems crash, much more often than we'd like. In fact, your iPhone sometimes dies in the middle of some computation. You have to reboot it. So does your tablet, so does your PC. It shouldn't crash. So ideally, it should run forever, but we don't really know if we put out an operating system. In fact, if Microsoft knew that it would crash on certain conditions, that would fix it before they would put it out. That's assuming good business practices. Your mileage may vary depending on which company you get your software from, but still, you don't want the program to crash if it's an operating system. But it's not clear if it does or not if it's complicated enough. So you might say, okay, for simple programs, you can tell very easily that this one runs forever, and this one stops, and this one you're not sure because it's 100 million lines of code. So you might think to yourself, size matters. It's because of the size of the program it makes it difficult to determine if it crashes or doesn't crash, if it halts or if it doesn't halt. And I'm here to tell you that size doesn't matter. It's not about the size here. And let me show you examples of this. So take this program here. It's a pretty short program, but basically it says a to the n plus b to the n is equal to c to the n. Find such an a and a b and a c and an n for n bigger than 2. So you can have a triple loop or a quadruple loop dovetailing between all a's, b's, c's, and n's bigger than 2. And if it finds a triple like that with exponents bigger than 2, it will print it out and stop, right? So how many say this program will stop eventually and print out such a triple, n bigger than 2? How many say, no, it won't, it'll look forever? Okay, so we had a bit of a split vote here. So those who said no, why are you saying no? This program will run forever, not find such a triple, not stop, keep looking.
I feel like I trust that Fermat actually proved it, even if we don't have access to them.
Yeah, so this is based on Fermat's last theorem. And Fermat's last theorem was basically that there's no such triple of integers with the exponent 3 or more. There's no such generalization of the Pythagorean theorem in integers. Now, if n is equal to 2, there's plenty of triples like that, right? 3 squared plus 4 squared is 5 squared, right? 9 plus 16 is 25. So that's an example of a Pythagorean triple. There's many more. In fact, there's an infinite number. But if the exponent was 3, there are no triples like that, and that's what Fermat says in his famous theorem, and Andrew Wiles in 1993 proved it, a mathematician from Princeton University. And this was open for 350 years, since the 1600s when Fermat stated this theorem. How many heard about that? It's a famous open problem, right? Finally settled after 3.5 centuries of it being open. It was such a difficult problem that in false attempts to solve it, that failed, still these attempts created whole new sub-areas of mathematics as a booby prize, as a side effect. That's how hard the problem was. A lot of math was created in trying to prove or disprove it without success for 3.5 centuries. So this will run forever, and it took us 3.5 centuries to figure out that this piece of code runs forever. Because this piece of code is equivalent to the statement of Fermat's last conjecture, now a theorem. And it took humanity 3.5 centuries to figure out that this piece of code does run forever and does not stop. And by the way, how big is this piece of code? Look at what it's doing. It's just trying to find integers a, b, and c, and n that satisfy this simple equality. How many lines of code do you say this is? How many say you can implement it in an afternoon? Good, most of you. How many lines are we talking about of code? Just approximately. I'm not asking for an exact answer. 7, 8, 9, 10, a dozen lines of code or like, yeah. How many see a dozen lines of code or so will do the job? Maybe 20 if you're not very thrifty in your use of lines. So we're talking about a dozen lines of code here whose halting, non-halting status took all of humanity 3.5 centuries to determine. So again, why am I saying this? To show you that it's not about size. It's not about code size, length of program. It's not at all about that. And illustrate that again, here's another piece of code that basically tries to find a prime number, an even number that's not the sum of 2 primes. An even number that's not the sum of 2 primes. So it'll go through all even numbers, and for each even number, look at all the primes less than it, and see if an even number is equal to the sum of any two primes. And if it is, it'll keep going. But if it's not, if it can't find an even number that's the sum of two primes, it will print it out and stop. Well, there's a conjecture like that called the Goldbach conjecture, right? And it's still open after a long, long time, right? It's been open since 1742. So almost 3 centuries now, nobody knows if this is true or not. We know that every even number that we looked at, that we tested, is the sum of two primes. So for example, 12 is 5 plus 7. 5 and 7 are prime, and 12 is a number that we partitioned into two primes. 20 is 13 and 7. Both primes, and they're equal to 20 when you add them up. And it turns out we've tested that for the first 10 to the 18 or 10 to the 19 different integers that are even. We tested it up to a trillion, roughly, and we didn't find any counterexamples. But nobody knows whether a counterexample exists or not. It's still open. So this piece of code here tries to find such a thing. Whether it holds or not is equivalent to the truth of Goldbach conjecture, this 300-year-old open problem. And we still don't know. How many lines of code are we talking about here, roughly? Take a wild guess. How many say you can implement it in a day? Sure. How many lines of code are we talking about? Just for the record, roughly. I'm not asking for an exact answer, obviously. 100, 1,000, 10,000 lines of code?
Maybe 100, because it's hard to find prime numbers.
Maybe 100, because you're saying, how do you find prime numbers fast? How many lines of code to tell if a number is prime or not? I give you an integer n, ask you is it prime or not. How many lines of code are we talking about there? Roughly, just roughly. 10 or 20 lines? What if you just do it the hard way? So I'm not asking for an efficient algorithm for primality. Do it the hard way. 3 lines, right? Primality testing, 3 lines. Go from 1 to n, divide by everything less than it, see if it divides evenly. Otherwise, you're done. It's prime. Right? So we're talking about 3 or 4 lines for primality testing. Not hard. I just want to make sure you understand. So how many lines of code total are we talking about here, now that we know primality testing can be done in 3 or 4 lines? 100, 1,000, how many lines? Maybe 20, maybe 15, just a dozen or two, between a dozen and 2 dozen lines. That's it. And the halting, non-halting status of it was open for almost 3 centuries and is still open. So again, it's not about size that makes the halting problem hard. Don't get me wrong, size doesn't help. If you have a huge giant program with 1 trillion lines of code, and some operating systems have hundreds of millions of lines of code, maybe even 1 billion lines of code by now, size doesn't help at all. Size makes it more complicated. But big program, it's not easier, it's harder, because there's more going on and all sorts of moving parts that you have to keep track of. That's harder. But even for short programs, it's plenty difficult to the point of impossibility. And one of the observations here, you can see where this is going. Arbitrary mathematical statements can be embedded in very short pieces of code, and the truth or falsity of the mathematical conjecture, however long it's been open, depends on whether this very short piece of code halts or doesn't halt because of these kind of embeddings of arbitrary math conjectures in just a few lines of code. How many get this insight here? It's a very subtle insight. It means the halting problem is as hard as doing arbitrary math. This is what we're saying here. That's how hard it is. We can couch arbitrary, difficult mathematical problems as small pieces of code with respect to halting and not halting. And that will settle arbitrarily complicated, long-standing open conjectures. So the halting problem is at least as hard as all of math. And math is not easy. It's actually harder than that, because a lot of things in math are perfectly doable. They're just difficult, but they're doable. The halting problem is not doable at all, and that's what we're about to prove with this prelude. Yeah?
Does the heat death of the universe count as termination?
The heat death of the universe, is that termination? Boy, I'd love to answer that, but that'll open some can of worms. So when we talk about termination, we talk about mathematical termination in terms of state changes and so on. If you talk about the universe having some definite end, like the Big Crunch that will lead to another Big Bang, or however you want to think about it, that doesn't impact these mathematical functions per se. Okay, but let's just leave it at that for now. Other questions? Yeah.
Do you have a compiler that can throw a warning if your code was equivalent to some library of known unsolved problems, or is that
Sure, assuming you can he's asking, can you have a compiler throw a warning if it's equivalent, if the piece of code you're trying to feed it is equivalent to some known problem. You can hard code a few known problems like this into the compiler, but even for a single known problem like this one, you can have many, many short pieces of code. All of them are equivalent to this, but they look nothing like each other. Just different implementations. One is recursive, one uses arrays, one uses another data structure, one is in C, one is in Python, blah, blah, blah. So you can have an infinite number of implementations of this, and you can't possibly program all of them into the compiler. And worse than that, given two short pieces of code, or any pieces of code for that matter, the question of whether they're equivalent, that too is undecidable. So the compiler can't even do this job in order to determine the other undecidable job, because that too is undecidable as a subroutine. So it's worse than that. Okay, so there's other interesting open problems to this day. This one, the question of whether you take an integer, if it's even, divided by 2, if it's odd, multiply by 3 and add 1. And the question is, for any arbitrary integer, if you keep applying these two operators, very simple arithmetical operators, to the integer repeatedly, will you ever get to 1 or not, or will it cycle forever? Seems obvious, seems simple, open question for a long time. It's been open for almost a century now. So things about termination, it's just very difficult. So now we're going to prove the halting problem. So this is probably one of the most elegant, beautiful proofs that I've ever seen in my life. And it's relatively short. It will fit on one slide, amazingly. And it was completely unbelievable when Turing presented it. Some people didn't even believe it when they saw it. It's that subtle and surprising. Okay, so the halting problem, again, we're proving it's uncomputable, undecidable. There's no algorithm for it. So h is this supposed function. We'll call the algorithm that supposedly computes it, we'll call it S, and we'll make it a black box, right? So in comes a program and an input, and this black box inside which supposedly there's an algorithm. Towards contradiction, we'll assume there's an algorithm inside this black box S. But it decides or determines whether the program and that input halts or doesn't halt. And if it halts, it says yes, and if it doesn't halt, it says no. And either way it stops, either way it's correct, and either way it finishes in finite time every single possible combination of inputs P and I. So it's always correct, always in finite time, determines whether the program P will halt on input I if it ran on I. Now, it doesn't mean that S has to run P on I. How many get that? It doesn't mean it actually has to do the running. Why? Because, I mean, just like here, in this examples here, you knew that this halts and this doesn't halt without actually running it. If you were forced to run it as a way of determining whether it halts or not, you'll never get this one. Because you'll run forever, and then you'll never know, and you'll never come up with the answer. How many understand that? So it's important, okay? So we're not saying that S here has to run P on I. It just has to determine that if P ran on I, whether it will halt or not. That's what S is doing. Okay, so that's supposedly, towards contradiction, the subroutine that presumably solves the halting problem will show that very quickly a contradiction will arise, and so S cannot possibly exist as an algorithm. So I'm copying S over here, no tricks, and I'm putting a little bit of fluff code around S. We're going to call it T. T will call S as a subroutine. You can call subroutines. In fact, if you couldn't call subroutines, computer science will be very ineffectual, right? You have to do everything from scratch. Every time you want to multiply numbers together, you'd have to do it the hard way using long multiplication and machine code rather than just call a subroutine that just says multiply, right? So T calls S as a subroutine, and T has its own input, call it X. These are all strings, by the way. X is a string, P is a string, I is a string. Of course, you can interpret a string as a program. You can interpret a string as an input. You can also interpret string as a stage play, if you'd like, and some string will look like Shakespeare's Hamlet, right? But that's an aside. I'm just driving home the point that everything can be represented as a string. So there's no type errors here. X goes in, T takes X and feeds it into S, both as the parameter P and the parameter I that S expects to see. These two strings that S expects to see as input. right? And then S does its job interpreting P as an input, P as a program, and I as an input, and asks, does that program would halt on that input, and says yes or no, always in finite time. And T does that, calls S. S comes back with the answer, yes or no, and if T says that S said yes, T goes deliberately into an infinite loop. An infinite loop is easy to deliberately walk into. While true, begin, end. We already saw an infinite loop a couple of slides ago, right? Very short, very simple. If T says that S says no, it stops immediately, and that's it. That's how T works. So how many understand how T works altogether, using S as a subroutine? That's all it does. It's just a few lines of code wrapped around S, the call to S as a subroutine. Now ask yourself, if you feed T to itself, will it halt or not halt? And that's a fair question, right? A compiler takes a piece of code as input. We already said that. But one specific piece of code is the compiler itself. So the compiler could be called with the compiler itself. You can call it on itself, and it actually makes sense for a compiler to compile itself. How many understand that? There's nothing mysterious or illegal about doing that, right? So we can call T with itself. So if T is called with itself, X will be equal to T, right? That's the input to T, right there. And P will be equal to T, and I will be equal to T, because both of those are assigned to X. And then so S will ask, what does P do on I? But both P and I are both equal to T, because that's what you call T with. So it'll ask, what does T do on T? S will ask that. And if T on T halts, S must say yes, because it's always correct. T will see that yes and immediately walk into an infinite loop on purpose. How many get that? Okay. And that's not so good, because if T on T halts, that means that T on T does not halt. So all we can hope for is that the alternative won't be so bad and convoluted as this outcome. So if T on T does not halt, P and I will both be equal to T. S will ask, does T on T halt? But it doesn't, presumptuously, right? And if T on T does not halt, S will say it won't halt, stop, give us that answer. T will see it and immediately halt, and therefore T on T will immediately halt if it doesn't. So together, these two things form a contradiction. It's something of the form Q if and only if not Q. And that's a contradiction. That can't happen. That's a bad day for logic, when you can prove a contradiction. So one of our assumptions must have been false. This is a proof by contradiction. Which assumption have we made here that's not obviously true? We made the assumption that S exists, algorithmically solves the halting problem. Okay, we made the assumption that if you have a subroutine, you can call it. We made the assumption you can take one parameter and feed it as two parameters into some subroutine that accepts something of the same type as that one parameter. We assume that if you see a no, you can immediately stop based on it. We assume that if some subroutine returns a yes, you can immediately, deliberately walk into an infinite loop, execute an infinite loop, and not stop deliberately. These are really all the assumptions we made here. I mean, I suppose we also made assumptions that code exists, and you can execute code, and so on. But those are pretty straightforward, obvious assumptions. There's nothing wrong with that. We do that every day of our lives as computer scientists, right? Write code and execute code, and code does stuff, and okay. So the only assumption here that's not obvious, that's not trivial, is that S exists as a piece of code, as an algorithm, and always does the job and always solves the halting problem correctly for no matter what you feed it as inputs, P and I. And that's the assumption that's false. It cannot exist, at least not as an algorithm, okay? And if you look carefully at this, this is an instance of diagonalization. How many can sort of smell diagonalization going on here? Not in terms of a table, but in terms of logical diagonalization over truths becomes false and falses become truths. Halts become non-halts and not halts become halts. And something you need to meditate over, it's subtle. But diagonalization occurs here. It's a non-existence proof. We show that there's no algorithm whatsoever that can sit in this box and do that job. So we showed we're not millionaires. That's hard to do. There's Turing smiling and your Cantor smirking, because this is the work of Turing, all right, out of his 1936 paper that changed our world. And it was based on the work of your Cantor, who pioneered transfinite arithmetic, and in particular the diagonalization argument that this is based on. End of proof. How many get this? Okay. Any questions? This is subtle. It's not long, it's one slide, but it's very subtle and almost unbelievable that this is true. Yeah. Question up there. Explain what? So diagonalization is you go over a bunch of things and you negate those things. Usually it comes from a diagonal of a table, but it doesn't have to. It can come up in other scenarios. So here, there's a bunch of results that S does. And T takes all of these results over all possible inputs to S and does the opposite of what S does each and every time. If S stops and says yes, it deliberately does the opposite and goes into infinite loop if P halts. If P doesn't halt, it deliberately halts. So that's sort of where the diagonalization is buried here. So this means that there's no algorithm that can sit inside the box S and do its job. Not possible. Ask me more questions, because this is a weird, strange result, and it's really an unbelievable result. Now, I've seen this result for decades now, and it still seems weird and odd and bizarre to me, except I know it's true. Yeah. The I? The I is just an input. It's a string.
No, but in the particular case of when you're doing computation.
So you mean this I here?
Yes.
So remember, S takes two parameters, P and I, they're both strings.
Right.
P takes a single string, X, and sets P and I equal to X, and then feeds both of those into S as S's own parameters, P and I. In other words, whatever string T gets, it feeds into S as P, and also feeds it into S as I as well. And it's okay to do because they're both strings. All three are strings, X, S, and P. X is a string, P is a string, and I is a string. So there's no type clash or anything invalid going on here. It's perfectly okay to do. More questions? This is a strange result. This shows you that an algorithm cannot exist, not just for us, not just in 1,000 years from now, not even 1 trillion lines of code, it won't exist, but an alien, wise, omniscient kind of race of beings halfway around the galaxy have been around for 1 billion years and can do all sorts of amazing things like terraforming and entire planets and world. They can't do this either. They cannot solve the halting problem either, not algorithmically. Okay. Now, aside from saying what this is doing, let's say a couple things about what this is not doing. So this is not saying that there's no magical creature that can sit inside this box and do the job using magic, like a gnome or an elf or whatever your favorite magical creature is from, whatever favorite movie that uses magic, or some Harry Potter character with a magic wand that just, magically waves the answers into being. We're not saying that. That is not contradicted by this result, but this mathematical theorem. What we are saying is there's no possible algorithm to do this job. Not that there's no magic or some deity or some divine power, but if there are, those cannot be made algorithmic. Those are beyond algorithms. And algorithms is all we got as a species, right? An algorithm is a very general thing. It's a set of instructions on how to do something. It can be as complicated, as convoluted, as deep, as sophisticated as you'd like. Everything we do is algorithmic, including what we do in our everyday lives. We get up, we brush our teeth, that's an algorithm. We go take a shower, we get in our car, we have breakfast, we cook according to recipes. A recipe is a subroutine in your daily algorithm. You call the subroutine, you make your breakfast, and blah, blah. Everything you do in life is an algorithm. And everything you do with computers is an algorithm too, right? We're saying no such set of instructions can possibly exist to solve this problem. And that's an amazing result. It's amazing that it's even provable, frankly. Such a strong negative result. Question? Yeah.
I'm a little confused on why you define T to go into infinite loop.
So she's asking, why do you want T to go into an infinite loop here specifically? Anybody want to answer that? The short answer is because it makes this proof work. I mean, you could have T do something else here. When it sees a yes, it can go and, go and, shop for a camera on Amazon. I mean, I'm not being facetious. I'm saying it can do something else. It can send a text message to you. It can just, play a round of tic-tac-toe. There's nothing prevents it from doing that if that's how you want to define it. It just won't make the proof will not hold, though, and the theorem will not be proven. Nothing terrible will happen.
So then, does the proof, more depend on our definition of T? I can't quite,
Good question. So she's asking, well, then doesn't the proof depend on this definition of T? Doesn't the proof is only true for this T, but not for some other T? Well, remember what the proof is. The proof is not about T. The proof is about the existence of S as an algorithm. So somebody gives you S and claims that S works. You come up with T to show that it doesn't work, that it can't work. And it's your choice what you use to show that S doesn't work, namely that T. If you showed a different T that just plays a round of tic-tac-toe, great. You have a tic-tac-toe program, and you haven't proven this, and nothing terrible happened, you just don't have a result. S is still undecidable, you just haven't proven it. But with this particular T, that knocks down S as a viable algorithm to solve the halting problem in each and every case, no matter what S is supposedly constructed as. Now, why didn't I say S is written in C? I was careful not to say anything about the algorithm in this black box that supposedly exists. If I said S is an algorithm in this black box is written in C, the C programming language, then you can conclude that maybe there's a Python program that does the job. Or maybe there's a machine language, maybe there's a JavaScript program that does the job. What if I said that S is a program, pick your favorite language, but it must use arrays as a data structure? Then what would you conclude? That there's no program that uses arrays to solve the halting problem, maybe one that uses binary trees that solves the halting problem, or some other database or whatever. So I was careful not to make any assumptions, not to be presumptuous about what's inside S. I gave it complete freedom to be anything it likes as long as it's an algorithm. I was very deliberate and intentional about that. Okay, any other questions? Yeah?
So this could be an algorithm or a program or a Turing machine. What could you define as like magic? What could you initially define S as magic and say you can't use it?
Oh, because if S was magic, then all bets are off. There is magic that determines the halting problem. What are all the solutions to the halting problem? What kind of objects are they in each instance of P and I? It's a bit. And some infinite bit strings will be exactly all the correct solutions to the halting problem. Does that bit string exist right now? How many say yes? How many say no, that bit string doesn't exist? Oh, good, I'm glad I asked that. There's a split vote. And the answer is either it exists or doesn't exist. There's no half existence in mathematics, right? So think about that bit string, that's all the solutions to the halting problems. Yes, no, no, yes, yes, no, no, yes. And it's an infinite length string. How many say that bit string exists? All right, and some people are saying yes. How many say it doesn't exist? And some people are saying no. Interesting. So half of you will learn something new in the next 30 seconds. That's good. That's why we're here. So anybody want to argue yes or no? Why doesn't it exist or why does it exist? This infinite bit string of yeses and nos.
Would it go on forever?
Of course it can go on forever. It will go on forever.
Right, so then, I mean, I guess you could have, I would say it exists then.
He says it exists. I agree. Why does it exist?
Because there's a solution to it, whether you can compute it or not.
No, it's even simpler than that. There is a prime number bigger than a Google. There is a prime number bigger than a Googleplex. How many believe that? How do you know? How do you know that? Because there's an infinity of primes, and many of them will be bigger than any number, including a Googleplex. So all these primes bigger than a Googleplex, they exist. Can anybody name a prime bigger than a Googleplex right now? No, the human race doesn't know of one right now. The biggest prime we know is roughly 2 to the 50 million or so. That's it. Well, it's a big number, but nowhere near a Googleplex. But that number exists whether we know it or not. So that bit string does exist. Moreover, every single infinite bit string exists in math. How many believe that? Every single bit string, no matter, in all infinite bit strings, they all exist. In particular, that one exists too, because this is one of them, and they all exist. What does it mean for it to exist? It's out there somewhere. Whether we know what it is or not, that's a different question. Just because you don't know of a prime bigger than a Googleplex doesn't mean that prime doesn't exist. It certainly does exist, and we know that for sure. Just because you don't know of something doesn't will it out of existence. If that was the case, most of the universe would go puff right now. Right? Think about that. Now, an integer between a quarter and a third, that one doesn't exist. It ain't there, for sure. So you have to clear up in your mind what it means for something to exist or not exist, and what it means separately from that for you to know its value or not. Those are two separate matters, and one is not the same as the other. On a good day, they coincide. Existence and you knowing what it is. But on an average day, they're not the same thing. It could exist and you may not know what it is, like a prime bigger than a googolplex. But it still exists. An integer between a quarter and a third does not exist. Okay, and keep that clear. All right. We'll keep talking about this stuff next time. Very important stuff. You can meditate over this for days, for years. Read about it in the book. It's important. All right, and there's an assignment due tomorrow, and the next one is already posted. So see you next time.
I had a question about one of the questions on the homework had kind of similar to what we did today with the like the number of Boolean functions that like